So we're on page 98, and what we're going to do here is go through the notes on the definition of the square root of a, and then we're going to look at a number of examples. So examples 1, 2, 3, and 4 from page 98. Okay, so we go first of all to the note here on roots and radicals, page 98, and it's topic 18. If the number is greater than 0, in other words, if it's a positive number, the second root of a is called the square root of a and is denoted by this here, the square root sign. And this implies a little number 2 up here, but we usually don't write it in, and is taken to be the positive square root of a. Positive is also called the principal root. The negative square root of a is given by minus root a. Also, a is undefined if a is less than 0. So if we're taking the square root of a negative number, it is undefined. The square root of a negative number is undefined, and the square root of 0 is 0. So, first of all, here, if we go over this, square root of 4 equals 2, since 2 squared equals 4. Remember, we talked about this being the opposite of it. This is where we raise the number, and we want to reverse this operation. The square root of 4 is 2. Now, if we want to get minus 2 as the answer, we have to take minus the square root of 4. Square root of a negative number is undefined right here. This is a negative number. It's undefined. Now that's the square root. Now here we're talking, this little number here means cube root. And what we're asking is, what number, when we multiply it by itself 3 times, gives us minus 8? And the answer is minus 2. Because minus 2 times minus 2 times minus 2 gives you minus 8. And here's another way of saying it, minus 2 cubed equals minus 8. When this number is 3 here, we call that the cube root. Here we're asked for the fourth root of 16. It's 2, which means that if we take 2 as a base and raise it to the power 4, we get 16. Now, just a little, here's a little piece of information that we'll review in part F. Square root of 2 approximately equals, this means approximately equals 1.414. If you put it in the calculator, you will get this. Of course, you may get other digits. Now, we call this number an irrational number. We discussed irrational numbers on page 1, but we're going to go over it. So you need to go to page 1, but we're going to go over it right now. These are numbers that are non-terminating, non-repeating. So here, this designation means the square root of 2. Here, I just rounded it off so that there were 4 digits. But if you just keep on continuing here, you get 0.414, 2, 1, 3, 5, 6, 2. And these dots indicate that the number doesn't terminate. So there's no repeating here, and the number doesn't terminate. If that's the case, we call it an irrational number. Well, you say, well, if that's an irrational number, what's the opposite of an irrational number? Well, a rational number are terminating or repeating. These are numbers that either end or they repeat digits. And they can be presented as the ratio of integers. So you can define a rational number as the rational ratio, A over B, where A and B are whole counting numbers, like minus 22, 24, 3, 5. The key thing is that a rational number cannot be defined where the denominator is 0. So you can't use 0 down here. So a rational number is a ratio of integers. For example, 5 is 5 over 1, which is really 5.000. The number terminates here. So that's a rational number. In this case, here we have the ratio of integers again, like we did over here. These are integers. Take 9 over 7. In this case, the number doesn't terminate, but it repeats. We get 285714, 285714. So the numbers 285714 keep repeating. Sometimes we indicate that with a line above the numbers that are repeating. So in the case of a rational number, the number terminates or repeats. In the case of an irrational number, they don't terminate and they don't repeat. So we go back over here, we can see that this number, which is really 1.41421, just keeps on going, and there's no terminating. The number doesn't end at any point. There's no 0 here that comes in. And so now, one thing that we said over here was we talked about the positive or principal root. I'll go back to what we discussed on page 97 and just review that right over here. Note that the value of the simplified radical is positive. While either of +2 and -2 might have been squared to get 4, square root of 4 is defined to be only the positive option. Okay, +2. When we do the square root of 4, the answer is +2. When you solve the equation x squared equals 4, you're trying to find all possible values that might have been squared to get 4. But when you are simply simplifying the expression square root of 4, the only answer is 2. This is the positive result and is called the principal root. The source for this is Purple Math. Here I've given it to you, and you can go and look it up in more detail. So now, if we're on page 98, we go to example 2. It says simplify using the product rule. So here, what we're got the square root of 3, square root of 16, and this is equal to 3 times 6 under the radical sign. Notice that the index, they're both square roots, so I can multiply. There's an implied 2 here, there's an implied 2 here. So what we're doing here is this part here, the product rule, square root of 3, square root of 6, equals the square root of 3 times 6. You can go back to page 97 and look at that. So 3 times 6 is 18. Now we're going to break 18 into 9 and 2. Why do we do that? Because 9 is a perfect square. It's 3 squared. So I can isolate the square root of 9 times the square root of 2, which means I'm reversing this and going from right to left. I'm going in this direction. I'm breaking 18 down to 9 and 2. Square root of 9 is 3, and I get 3 root 2. Now, this simplifies, but you see this was not a perfect square, and this was not a perfect square. I asked myself, is 18, can I get something out of 18? Can I break it down into 2 numbers, one which is a perfect square? And the answer is yes, 9. And I take the square root of 9 is 3. Cube root of 40. Now I ask myself, can I break down 40 into something where I can take the cube root of it easily and get an integer? Well, I can break down 8 times 5, that's 40. And now I can break this down into the cube root of 8 here times the cube root of 5, where essentially what I'm doing is taking this and going in this direction. So I break this down. Now why do I do that? Because the cube root of 8 is 2. I leave the cube root of 5 here. So when you're doing these kinds of problems, what you try to do is isolate a perfect square, perfect cube, whatever, depending on what the index is right here. Here the index is 3, here the index is 2. So in part A, the most important part is to isolate the square root of 9 right here and realize that it's 3 squared. In part B, the most important part is to isolate the 2 cubed, because the cube root of 2 cubed is 2 to the 3 over 3, which is 2, which was what we did over here. So we went from the cube root of 8 to 2. Now here we're going to apply the quotient rule, and so we have the square root of 14 over the square root of 7, and we're going to bring this under the square root sign and put both numbers under there. 14 over 7, 7 goes into 14, 2, and we get the square root of 2. So you can see what we're doing is going from left to right. And here what we're going to do is reverse the procedure. The square root of 49 over the square root of 100 equals, and we're going to take the square root of the top and the square root of the bottom. So we're reversing this. We're going from right to left. See, we've got this under the square root sign, which is this here, and we're going back to this kind of a designation here. Why? Because the square root of 49 is 7, the square root of 100 is 10. So we're using the quotient rule here, which was the rule that we saw on page 97. Okay, so now we've got problem 4, 4 square root of 5 plus 3 square root of 5. And in this case, we're going to factor out from both these to get this answer of 7 square root of 5. We're going to factor out the square root of 5 from the first term. If we multiply 4 times root 5, we get 4 root 5. If we multiply 3 times root 5, we get 3 root 5. Now, we factor out the root 5, and we're left with 4 plus 3. We add the 4 plus 3, and we get 7. So this simplifies to 7 root 5. Now, in this case, got the square root of 75 minus the square root of 12. Now, what we do with the 75 is to realize it's 25 times 3, because 25 is a perfect square. We change the 12 to 4 times 3, because 4 is a perfect square. It's 2 squared. 25 is 5 squared. So you see, when we have 25 times root 25 times root 3, that of course is root 75. And instead of writing square root of 25, we write 5, and the square root of 3 is right here. Okay. Now, what we do with the second term here, minus 4 root 3, we isolate this as square root of 4, square root of 3, square root of 4 is 2, that's that number here, and then we've got 3. Now let me say that you can, if you want, just go directly from this to this. You don't have to go through this step if you see it, but it's up to you. So now what we're going to do is we've got 5 root 3 minus 2 root 3 equals 3 root 3. If you want, you can just factor out the root 3, which is right here, and you got 5 minus 2, so you get 3 root 3. You could say, well, this is 5x, and this is 2x. If you make the x equal to root 3, 5x minus 2x is 3x, and the x is root 3. So you can do it that way if you want. So this is just now what we've done on page 98 is to review the rules that we used that we saw on page 97. So that completes page 98, our discussion on page 98.